play my own game. Come on, score. Well, it doesn't look like one, but it is a computer. And it just shows what can be done when a computer is designed specifically to produce good graphics and sound. Now, playthings like this show us something that's likely to become very important. The future of computing is not just going to be screens full of figures and letters, but sound and moving pictures.
Well, I've climbed hundreds of mountain peaks in my life, so I suppose I have a real urge to stand on top of the world. Well, this time, I'm not standing on top of the world, but I am stood on top of the sky. I'm stood on the roof of the London Planetarium, and inside is a representation of the night sky. At the centre of the auditorium is a complicated projector that throws pinpoints of light showing satellites, stars, planets and nebula onto the inside of this globe. This amazing machine has 29,000 parts. It's got 200 optical devices that can project 8,900 stars onto this huge screen. The projector is simply an optical device throwing patterns of light onto the dome. In a similar way, a computer can control the computer has options.
Wonderful pictures, but to the computers which produced them, they were nothing but numbers describing which points on the screen to light up, when and in which colour. But how do you get the numbers into the computer in the first place? Well, you could feed them in through a keyboard in the usual way. But if you look at the picture I've got on the screen here, you can see that would be very tedious. You'd have to type in every single position and every single colour and so on. So all kinds of devices have been developed to make the job easier. This one, for example, is called a graphics tablet. And if I draw on it with this cursor, what I draw normally is reproduced on the screen and stored away in part of the computer's memory. So it can be used like a paintbrush. But unlike any paintbrush, the computer will remember shapes and colours. And we've asked this one to remember a bird we drew earlier, and I can fill the sky with them just by moving the cursor and pushing the button. Let me show you what I mean. There's a little flashing dot of light, which you may just be able to see as I move it around with the cursor. And then all I have to do is press the button and fill the sky with birds. In an animated cartoon like our computer owl, it takes a large number of pictures to move an object or a character smoothly from one position to the next. Now, is that something a computer can help us with, Mac?
Yes, it can, and even surprisingly, quite a small micro can handle it. For example, from this little shoot here up to a full blade of grass, we'd want to put all the intermediate growth in. But all it's really doing is taking the final picture and the start picture, drawing lines in between the two, and filling them in bit by bit.
Well, that's in principle exactly what happens with the in-between pictures, which are normally laboriously done by hand. Is a computer capable of doing that for a proper full-blown animation?
Yes, but it requires a much more sophisticated and powerful computer. For example, if you wanted to make the wings on your owl flap, the computer would have to know something about how an owl's wings actually flap, and it doesn't necessarily flap in one straight line. Of course, the computer doesn't recognise these shapes as such. All that it knows is the colour and the position of various dots. It can't tell what that picture is any more than that sweater knows about that rather curious owl you've got on your chest. By the way, I think I see a little loose end here, Chris.
Look what you've done to my owl.
I wouldn't worry about that, Chris. Look, it's all in here, and all you need is the code. You can reproduce it, or the knitting pattern. In other words, the order in which the stitches are going to go around, and you get the whole thing back.
Tell you what, Mac, you're the expert. Here you are. You do it.
Well, I thought you might say something like that. Well, it's clearly going to be quite difficult to re-knit that and see what sort of pattern emerges. So we've got something much simpler here. This is a plain stripe running down. Now, if we unravel this, like we did with your owl, and then re-knitted it again with a smaller number of stitches per line, per row, we get something like that, a diagonal running right across it. And if we vary the number of stitches per row in a rather formal manner, you could create yourself a little zigzag, and that's how patterns work in knitting.
Yes, the pattern says knit one, purl one. There's a whole list of stuff you have to follow. Now, is that like the computer program feeding a list of stuff to the screen to make it create the pictures?
Well, in a very similar sort of way, it will tell it which spot to illuminate with which colour as it goes across, and it produces different colours, and thereby producing a pattern that looks to us like a picture.
Right. Well, it's that ability to interpret a stream of information in the form of pictures and the ability to manipulate a design that makes computer graphics so useful in practice. Here's Jill Neville.
Just take a look at this bus timetable. It's a mass of times and names of places. With a bit of a struggle, I can work out what's happening. But how much simpler it would be if I wanted to know how to get from A to B if all that information were represented graphically in a map showing where the buses run. Well, that project was given to Magda, a design student at the Royal College of Art. And on the face of it, it seemed simple enough, merely a question of drawing the bus routes along the appropriate roads. But Magda came across an unexpected problem, with which she needed the help of Brown Smith and the computer.
She wanted to be able to draw parallel lines to show the ways in which the buses, when they met, followed a road and you maybe had 4 or 5 buses going along together. Now, her difficulty was that it's extremely difficult to draw parallel lines other than straight lines that you can use a pencil and ruler for. These lines had to actually go round, follow roads and go round bends and so on. And so we had to design a program that would actually let her put in the road as a line into the computer, digitize that in, and then the computer would produce parallel lines following it. Get the program running. Okay, now if you just put in a sort of gesture, if you like, with that pen on the bit pad and more or less follow that line.
Right, just to
Yeah.
follow
That's
that
right.
line.
And that'll come in on your screen over there. See that? And it said it can't divide by 0, and it stopped because it didn't like part of the curve that we drew in. Well, the first reaction was, here's another fairly easy problem to solve. I should have learnt by now, and I certainly did after that, that reaction is normally incorrect. The simplest looking problems take the longest time. In fact, I thought it would take about a day, and I told her that on the phone in the morning. It took 2 months in the end. The difficulty is that something which is very simple for a 3-year-old person to do is extremely difficult quite often for a computer to do. Something which is extremely hard for a person to do might be done in 3 seconds by a computer. Frequently you can't tell. It did take a long time. Now it's asking us if we want to put that out on the plotter. Well, let's see what that looks like anyway. So I'll say yes, we want to plot it. So yes, parallels, 2 lines again, and the same distance apart, let's say. And off it goes. We managed to get a program which would immediately produce parallel lines almost anywhere except that we wanted. The program would appear to be going all right. It was almost malevolent. It would follow part of the curve around and suddenly zoom off to the side and have its lunch and come back again. Sometimes about 7 of us around there, getting ready to thump it if it wasn't going to work right. This is anthropomorphizing it a little bit too much. The computer was doing exactly what it was told to do. The point is that I wasn't telling it sufficiently correctly what to do. As it made each mistake, we learned how to make it do better, and it, in essence, taught it what, of course, we were doing was teaching ourselves. And now it says it can't continue because having altered that line, it actually did interfere with the program. Let's try it quickly again. Right. Try it really quickly to draw a line straight across there. That's it, lovely. And then hit the stop box again. And it's working that out. It shouldn't take too long because it really is a very simple little curve. If it can't cope with this, I think we've had it. Now, it's joined on top of the old lines, we don't know. There's the first line. Is it going to do it? Yes.
Oh, wonderful.
Well, so far.
Oh, that's really nice.
And it did work, and here's the result. So the next time you're in the west of Scotland standing at a bus stop, you'll know how those parallel lines were drawn.
Well, of course, it's not hard to see how immensely valuable computer graphics can be for artists and designers and cartographers. But, Mac, what about the businessman? How does computer graphics fit into his world?
Well, the computers are spewing out so much information, so many numbers, that it's almost impossible to find out just what's going on. So people have been trying to produce graphs like this, which might be a pie chart showing market share and so on.
Normally with pots of paint and a brush.
Yes, it takes a long time, and that can be done on a computer. But if you get some numbers like this, if you get that list of numbers, it's very, very difficult to really analyse what's happening.
Yeah.
So to get that into a graph, we just hit a couple of keys, and you'll see the forecast coming up now in yellow, zinc. Those are the forecasts, and there you can see that he's been behind there and he's ahead there and so on. It's obvious what's going on.
So the yellow ones indicate what you planned for,
Right.
and the red ones indicate what actually happened.
That's right.
Right.
Now, the real thing is, if you want to update this and change it, and this is where this little mouse comes in, where you can pick these instructions on the screen.
By sliding about
By
on
just
this
sliding
flat
it about
surface.
on there. You have 3 functions on it. One is to pick, which is to select the instruction. One is to say it's done, you've finished giving it commands. And this one is just an error button to say you've given it the wrong one. And then you just move it. As you move it down, up and down here, it will move the cursor on the screen.
You're actually pointing that little target thing onto
At
the
those
things
numbers,
there.
and you can see those are the numbers we've got for the red bars, and we're going to put one after that little job there, and then we enter the value. So we'll put in, it only goes up to 800, so we'll put one in at 950 and see what happens. And that just shows you that it is correct and you've inputted it, so we've there ended. You can see it's rescaled here, it's put the actuals in, and there's a new piece of data that it's put in.
Right. Obviously, this is a fairly sophisticated business users type of thing, which would be certainly beyond my means, so expensive compared with a microcomputer. But is it the sort of thing that a microcomputer can do at all?
Yes, it is, and we can show you that. This one, which store 5,000 charts, but we can actually do on some really quite interesting stuff on a little micro like this. Now, what we have done is written a little program to put some scales on the side here, and that's a little subroutine we've written, and it's rather like the scales on some graph paper. The actual screen is just over 1,200 points along the bottom and 1,000 up. So along the bottom we're setting off or scaling up in hundreds, so 100, 200, 300 along the bottom, and 100, 200, 300 going up the side on these
So
cells.
January is 100, February 200, and so on.
Right, you could think of it in that way.
Okay.
And there's our little program that's going to do it.
Now, 10, the first instruction is go sub 500, so at position 500 there is that subroutine which creates that graph.
Yes, that's where it starts, this
Probably
subroutine.
a little more complicated than this looks.
Yes, it's quite a detailed piece of program, but not very difficult.
All right. Now, if a month equals 1 to 12, that means nothing to me.
Well, that's the start of what we call a loop, and that's really linked into this pink thing next here. And as a piece of protocol, we've indented here what's inside the loop that we're going to do a certain number of times. So you can recognise those two.
Indenting is a kind of convention that you
Yes,
do that,
just
so
a
to remind
convention.
yourself where the loop is.
Right.
OK. Print sales, easy. It'll print the word sales on the screen. Input sales is telling the computer to expect something called sales, which will be, in this case, a number.
Right.
Right.
Now, draw is another command you haven't seen before. So let's just go through it. For month 1, print sales, you will input the sales, and then it says draw, month 1 again, and this little star means multiply. So it's 1 times 100, so it'll go along the bottom to position 100, and then the comma, and then sales, it will go up to a point of the number where you've got sales, and it will join that to the 0. And then it says next month, so it goes round the loop, and then it goes to 2. So it's doing in steps from 1 to 12, in even steps, 1, 2, 3, 4, 5. So it goes 2, print sales, so you print sales for period 2, and then it draw 2 times 100, goes to 200, and it goes up and plots that point and joins it up to the last point.
And a lot of this is basic jargon, again, the language
Yes,
basic,
it's just
is that
basic.
Right? So if it seems puzzling, which it does slightly to me, I mean, once you've got the hang of the basic vocabulary, that would become more simple, seemingly.
Yes, the two things are always linked together. It's for months 1 to 12, for example, is always linked with something that says next month. So it always does the next month, and every month, but 1 at a time, up to 12.
Well, the proof of the pudding is in the eating. End is pretty obvious. So it's the end of the programme.
Yes.
That's a word I understand very clearly. Can we now run it?
Run it. Now it's asking you for sales in the bottom.
Right. Well, you want in multiples of 100, or rather in the hundreds, don't you?
Yes.
So let's say 500 to start with.
It's joined it
It's
straight
climbed
up.
up to, and that is 500.
It's gone to the point 100, gone up to 500.
Well,
and
let's
connected.
imagine that February was a bit too cold for people to buy ice cream, so drop it down to 250. And there it is. It's very clever. And this is the sort of thing that the average business user could use.
Oh, yes, very easily,
And store
yes.
away on a disk and keep
He could store it
updating
and
month
then
by month.
recall it every month and update the next point. And not only that, of course, he could just print it out on a printer. So if he wanted some copy, he could get it printed out on a little printer like this.
Right. So we need good graphics to help us understand the information a computer can give us. But we also need something else. Many people think that computers won't be really useful to us until they can speak. Well, that's something they can already do. You may well have seen the little speak and spell machine, little thing available in toy shops. And teach you to spell. We go for level of difficulty D. Are you ready for this? You want to learn how to spell, Mac?
Spell plunger.
Did you understand that
Why
word?
do the computers seem to sound like
I've
you'd
gone
expect
off it.
computers to sound like?
Would you say that again, please?
Plunger.
I still don't understand it. What does it say?
Plunger.
Plunger. Fine, that's quite enough of that. But how do you actually get the business of speech recognition and speaking into a computer?
Well, that's very hard to do. You have to break down the word. At least the current techniques is to break down that word into various sounds and intensities and so on. It gets very, very complicated. But we can do something even with a little microcomputer.
Even with a microcomputer,
Yes,
you can teach it to speak or
Yes, you can
recognize speech.
Right. Well, I've actually put in a couple of words on this.
Right.
And perhaps you'd like to try and teach it another one with this microphone. So
try.
it is in the teach mode. And as soon as it comes up, we're going to have to repeat it 6 times. So
Right.
it gets a profile of you speaking this word, and then afterwards we can see whether it will
You
recognise
want this
it.
quite close, don't you?
This is a very cheap little system, by the way. It's called Big Ears.
Hold that there for a moment.
Right.
Now it's,
So it's
T for teach or L for listen, is that right?
Teach. I'm going to teach it.
Okay, type your word.
Why not tomorrow?
Tomorrow.
Return. I have to be careful now.
Yeah. Tomorrow. 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 That was 6.
That was brilliant. Now we're going to see whether it will recognise our 2 voices. And I'll start with my 2 words, and then you finish with tomorrow and see if
Okay,
it works.
go on then.
Right. We're going to get it to listen. L. C. It worked. That's good. I didn't think it was. U.
Beautiful.
Your turn.
Tomorrow.
I think that's absolutely
Marvellous.
brilliant.
Well done, Mac. That's a marvellous programme, and it all in a little tiny box that size.
That's right. Well, you can imagine shouting, run at it, or open the door, and it would do
Yes.
things
Switch
for
on
you.
the central heating, pull the
Yes.
curtains, switch on
It's
the
a-
telly, boil the kettle. Wonderful.
It is a long way from dictating a letter into it and getting it typed out on a typewriter, but that will arrive one of these days.
Well, if real speech recognition, as Max says, is still in the future, and intelligible computer speech is expensive. Music from the computer is already here today. Perhaps you may have seen this little gadget. It'll play notes in different instruments. And so on. What's more, it can even remember a tune played on it and play it back to you days later. Of course, this little keyboard is on the fiddly side, but attach a full-size keyboard to a microcomputer and the result can be an instrument that is capable of even more different sounds than a synthesizer. Recording studios are now using quite large mini-computers to produce some of their special musical effects. But if you want to know how some of the stranger sounds on today's discs are produced, the answer, as often as not, is from a small computer like this.
Outside the immediately creative sphere, what does a computer have to offer the artist?
It operates on a couple of important ways, I think. One, its use simply as a tool, like a pencil or a chisel or an airbrush or a flamethrower, whatever people want to use in their work. You can get the computer to draw pictures on a screen. Above and beyond that, though, it can actually deal with the concepts that people are themselves dealing with when they're making art, so that if somebody paints in a particular sort of way, to get the computer to help them to do it, they have to look inside their own head, as it were, to understand how they make the marks that they make.